Hi everyone, today we'll give a brief overview of our paper at ITCS. It's called Learning Arithmetic Formulas in the Presence of Noise. So in our paper, we see that there are a few unsupervised learning problems like subspace clustering and mixtures of Gaussians, which can be reduced to this problem called robust vector space decomposition. And this problem is the main part of our paper. We define this problem, we solve it, and we also analyze the reductions from these specific unsupervised learning problems. So I'll go straight into describing what this problem is. So it's a very natural problem and it's easy to state. So here's the setting. So you have two spaces U and V, which are subspaces of the ambient space, and you have a bunch of operators between them. And this U, it's a direct sum of S subspaces, and so is V. And these operators connect to U and V in this way that each B in this collection, it takes Uj to Vj. So it takes the jth component to the jth component. And the problem is that if you're given U and V and this collection of operators, you want to find these summands, the Uj's and the Vj's, up to reordering. And of course, you want to solve this robustly. So if you're given U, V, and B approximately, you want to find the summands approximately. So there can be many ways of solving this. So I'll discuss our intuition. So let's call these operators in this collection B1 to Bm. And let's take a basis of U that respects this decomposition. So essentially, the first few vectors are a basis of U1, the next few are a basis of U2, and so on. And we stack this basis into this matrix M. And similarly, we stack a basis for V into N. And now, if you rewrite Bi in this new basis, because of this condition that each Bi takes Uj to Vj, these Bi's in this new basis are just block diagonal matrices. How this helps is that if you also look at the projections onto each of this Uj and Vj according to this decomposition, so basically they're just diagonal matrices under this new basis with identity at the jth block of the relevant dimension. So it turns out that the action of Bi on Pj is the same as the action of pi j on Bi. If you calculate just from these equations, they both turn out to be the same matrix. And even intuitively, this makes sense because each Bi takes the jth component to the jth component. So restricting the inputs and then applying Bi to the restricting the inputs to the jth space and then applying Bi is the same as applying Bi and then restricting the outputs to the jth space. So we see that these projection matrices, Pj and Pij, they share this special relation to Bi. And remember that this Pj is a projection onto Uj. So finding Pj is sufficient to find Uj's. So this is what we would like to find. And because of this special relation, one expects that if you can find all matrices D and E which satisfy this special relation with all the BIs, that is BID is EBI, then you might get a clue about what this Pj and Pij is, which will give you the Uj's and the Vj's. And this leads to the notion of the adjoint algebra. So like we just said, the adjoint algebra is nothing. It's just the space of all those matrices D and E such that they have this special relation to the matrices Bi. So BID is EBI for all I. And here are some facts. So this space is an algebra, which just means that in addition to being a vector space, it also admits a multiplication. So you can multiply two such tuples and naturally stay inside the space. And we saw that each projection matrix Pj and Pij, each such pair, it's in the adjoint algebra. And because it's a vector space, any linear combination of these elements is also in the adjoint algebra. Now, each projection matrix, it's a projection into disjoint subspaces. So each projection matrix is independent. So this means that the adjoint algebra has dimension at least S. And we call the adjoint algebra to be non-degenerate if the dimension of the adjoint algebra is exactly S. It just means that these the linear combinations of these matrices is all that the adjoint algebra contains. There are no other matrices. And it turns out that this is not a very strict constraint to put on the adjoint algebra. In fact, all the applications that we study, they satisfy this condition under certain assumptions. So with that, we have built the machinery of how we are going to attack this problem. So let's see how we can use the adjoint algebra to solve this problem when there is no noise. So to get a hold on the adjoint algebra, we define this operator called the adjoint algebra operator. It's nothing fancy. It's just an operator which has the adjoint algebra as its null space. And as you can see here that this operator kills a vector if and only if all these components are 0, which is just the definition of being in the adjoint algebra. And now if we pick a random element from this adjoint algebra, and if we assume that this adjoint algebra is non-degenerate, so this random element is P and pi, because of this non-degeneracy, this P we know has to be a linear combination of the projection matrices Pj. And somehow, from this P, we want to find each of these Pj's. And how do we do that? So we look at the multiplication operator P hat. So what is this operator? It just takes an x to Px. And we know we can do this because it's an algebra, so multiplication is allowed. When we look at this operator, now this operator is on a space of dimension s, to a space of dimension s. So this has at most s eigenvectors. And if we look at the action of p hat on each of these pj's, so if we multiply this to pj, we get a pj squared term. And because pj is a projection, pj squared is just pj. And we get pi pj terms. And when I is not equal to j, because these are disjoint projections, that's just 0. So p hat of pj is just lambda j of pj. So pj is an eigenvector of p hat. And because there are s such projections, so this just means that these projection operator pj's are exactly the eigenvectors of this map p hat. So this gives us a recipe of solving this problem of vector space decomposition when there is no noise. So let's just recall what this is. So remember, we have two spaces u and v, which are a direct sum of s subspaces, and we have a bunch of operators which sort of have some information about what this decomposition is, in this way that it takes the jth component with the jth component. And how we solve this is we construct this adjoint algebra map, and we pick a random element from its null space. The null space is just the adjoint algebra for this collection. And we take the p part of this random element, we look at the multiplication operator p hat corresponding to it, and then we just output the column spaces of the eigenvectors of p hat, because the eigenvectors of p hat are just the projection matrices pj's onto these component spaces. So this is how we solve the exact version of the problem. For the robust version, what we just do is we adapt the same algorithm. We just need to find the right replacements for each of these quantities in the noisy setting. So here is how we do it. And not just that, we would also like to express the quality of the outputs of the robust version, which just means that given a certain error in the inputs, we'd also like to quantify exactly the magnitude of the error in the output that the algorithm produces. So for this, we need certain perturbation theorems, like we want to know how much do the eigenvectors of a matrix get perturbed when you perturb the matrix itself, and also how much do the null spaces get perturbed when you perturb the matrix itself, right? So because as we saw in the algorithm that the null spaces and eigenvectors, those are essential parts of the algorithm. So I'll not go into the details of this theorem, but we have these theorems. So we go over the algorithm again, and this time with the replaced quantities in the noisy setting. So we first construct the adjoint algebra map, but this time we have access only to b tilde and not to b. So we construct the adjoint algebra map corresponding to b tilde. And in doing so, the distance between these two adjoint algebra maps, it just depends on the distance in the input that we are given. And now this map, it may not have a null space. So the relevant quantity that the null space gets replaced by is the span of the s smallest singular vectors of this map. So we have the perturbed adjoint algebra here, and we pick a random element p tilde from this adjoint algebra. So because we are looking at how the null space of a map gets perturbed, here the null space perturbation theorem comes in. And we also know that we can bound the p tilde from the corresponding p in the adjoint algebra using this bound, right? And now we construct the multiplication operator, which is p tilde hat. Now there is a small caveat here that this perturbed adjoint algebra, it may not be an algebra anymore. So now multiplying p tilde to x may take x outside this space. So just to bring it back to this space, we equip this p tilde hat operator with this projection, which takes it back to this space. So this is our new p tilde hat. And of course, we are looking at the eigenvectors of this map p tilde hat. So here the eigenvector perturbation theorems comes in. And finally, we want to output the column spaces of these eigenvectors. And even that we can bound by our column space perturbation theorems. So finally, we using all this, we recover a uj tilde, which is close to the original space uj, and this closeness is given by these quantities. So there is the error in the input, and there is the condition number of m. So this quantity depends on the angles between the component subspaces, and of course, the random element that we pick, the eigengap of that random member of the adjoint algebra, that comes into play here, and we have some inverse dependency on some relevant singular values.